Hello and welcome to a half an hour summary of the OCR GCSE Computer Science Paper 2 exam, which I would say is deceptively content heavy. There's a lot of stuff in here to go through, so I won't talk for much longer. All I'll say is this is our practical paper and has a lot of stuff on algorithms, but also, like I say, some other bits of theory you've got to know as well. So this is just a summary. For more detail, look at my playlist, look at the description for other suggestions of how to revise this. Let's start with what this paper is all about really, which is algorithms. So an algorithm is a sequence of steps that can be followed to complete a task. And a term you may or may not come across is algorithmic thinking, which is really using algorithms. And so this is solving problems by defining these steps and the sequence needed. So what are the steps to solve this problem and how should we order these steps essentially? Now, program code is just implementing an algorithm, and as we'll talk about, you've got to know how to program in a particular language. You can also represent algorithms in pseudocode and flowcharts. That'll be in section A in particular. Pseudocode is just something resembling code, but it is often a bit more relaxed. How you do this doesn't really matter, as long as it looks a bit like code. Flowchart, though, has a set group of symbols you've got to know about, starting with the start and end symbol, which is a shape which looks like this. I won't try and describe it. A process box is a particular instruction. So we'll start with a start symbol, end with an end symbol, but you might have several process boxes. You should write inside what exactly this process is. And there are two kind of adaptations of process boxes. A subprogram, we'll look at a bit more later, but is a group of related steps essentially, and has the kind of two vertical lines. And a parallelogram is for input and output specifically. For selection and also for loops, you'll use a choice symbol where you put the decision inside the diamond, and this should be either yes or no or true or false. Your algorithm should be as abstract as you can while not getting too simplified. Abstraction is removing unnecessary detail from a problem. And a different technique which also helps simplify is decomposition. This is breaking down a problem into subproblems that each represent a specific task, and you might actually implement these as actual subprograms. One diagram you might see related to this is a structure diagram. So something like a social media app would be far too big a project just to dive in and solve. So you might decompose it into particular subproblems. And this is how you might represent that in a structure diagram. The further down in this tree structure you are, the more broken down that particular subproblem is. Trace tables can often be worth a fair few marks, and they show how values change when an algorithm is actually carried out. So just to give you some tips for these, make sure you go through every line of the code and follow every line of the code. Only actually add to a column when that particular column's value changes. Don't copy down loads of values all the time. And as a general rule, it's not always exactly true, but generally only move on to a new row in the table when you move into a new block in the code. So new selection, new iteration, etc. Lastly, because of these, you're going to have gaps most likely, and they are absolutely fine. So to give you an example of one, I won't go through it in line by line detail, but just as an example, let's say you're given this code, and because it's got user input, it might tell you the actual sequence of input, so make sure you don't miss that in any questions. So your job would be to be given a table like this and fill in every change to the columns. So the columns are often variables or items or outputs. You just write down every time it changes. Now just on that third tick, I would say these first three variables are in the same block of code as a sequence block. So personally, I would stick them in the same row. Whereas when you go in the for loop, I would certainly move on to a new row. I mean, you have to here, but I would anyway, because it's a new block of code. So here we're updating X and Y because of the if statements. And we keep going through. When 554 is entered, because it's not less than the current X, which is 355, it doesn't get changed. So X will stay as it is, and so therefore don't copy it in again, leave it blank. So you'll start to see some gaps potentially as you go through. And the final result, if you were interested, will be 199 and 554. This program would find the biggest and the smallest item in the user's input. So a common follow-up to a trace table is, what is this algorithm doing? And also often there'll be a logic error somewhere, and the trace table might help you spot that logic error because you might be able to see a value change when it shouldn't change. There are 5 specific algorithms you've got to know about, 2 searching ones. A search algorithm will just look for a target. Linear search is our most basic. Linear search will compare each item in a list one by one until the target is found. And crucially, there is no need for the list to be in order because it's just going one by one. So let's say I'm trying to find 5 in this list. Well, it compares 15, 17, 19, they're not 5, but it gets to 5 and finds our target. Right, that's how it works, one by one, simple comparisons. Binary search works by first of all comparing the middle item to your target item, and it will discard half of the list which the target can't be in. And it can do this because the list must be ordered in this case. Now, once it does this, if the item hasn't been found yet, it finds the next middle item and repeats this discarding and finding the middle item process until it finds the target or it runs out of items. So for example, if I'm looking for 5 again in this particular list, this time it's the sorted version of this list, I would start looking at a 17, which is our middle point, where 17 is bigger than 5, and so I can eliminate the top half of my list straight away. The next middle item happily happens to be 5 here, what a coincidence, and so this ends. If you haven't got a nice clean middle, then just choose either left of centre or right of centre. You'd much rather do binary search if you can because it's much more time efficient for linear search, meaning that as the list grows big, on average it takes less time to find your item, but the key disadvantage being it needs to be in order beforehand. Now you might decide to put your list in order through bubble sort, merge sort, or insertion sort. In bubble sort, it works by doing a series of passes. In one pass, it goes through the list and swapping each pair if it needs to. And it will go back to the start in the next pass and repeat this swapping of pairs until a single pass happens with no swaps. Well, let me show you this on an alphabetical list. Let's put this into ascending order. So we start in our first pass by looking at A and C, which are fine. You'd then look at B and C, which need to get swapped. You'd then look at C and E, which are fine. You'd then look at E and D, which need to be swapped. Now that is just one pass, and so it would keep going. Again, I've been very careful with how I've chosen these examples because in the second pass, there would be no swaps, and so therefore it would end. But there is always going to be a pass where no items get swapped, and then it will end. Merge sort has a couple of steps. The first step is to divide your list continuously by 2 until each list has one item in it only. So you keep dividing until you've got many individual lists with only one item in. Then you start to merge these lists. So you combine 2 lists at a time, keeping the items in order as you do this. So this time let's do it in descending alphabetical order. So therefore C should come before A and E should come before B. Now if you've got a odd number of items, it's a little bit awkward. You have to do it just 2 at a time, which means D gets left on its own here in this particular example. But you combine it 2 at a time and eventually you get your sorted list. Insertion sort starts with one item in a sorted part and moves items one by one from your unsorted part to the sorted part. Let's put this list into descending order. Well, I've got one item, 5, in the sorted part already. 17 is the first item in the unsorted part, so I move that into the sorted part before 5 because it's descending. 2 is the next one, which should slot in just to the right of 5, and then 9 needs to go between 17 and 5. So one by one, we're moving items into the sorted part and keeping the order the same. Moving on now to think about programming. There are 2 sections in the paper, A and B. In A, you're going to get mostly free choice when you answer algorithm questions, so you can really answer it in your own way. Whereas in section B, there might still be some free choice, but most it will be more restricted. So for some questions, you've got to answer in a programming language, either a real one, which you've learned in class, or a fake one, which is OCR exam reference language, ideally. In all of the examples to come, there'll be an OCR exam reference language, but if you know the equivalent in your language, that's great. In fact, I think that's better. So data types. Data types are there to determine how data is stored in the computer and also the operations it can do. And there are 5 you need to know about. A real is a fractional number. It's also called a float quite often. And yes, if it's got quotes around it, effectively it must be a string. So no matter what it is, if it's got quotes around it, it's a string. Now, you may need to cast between different data types. This is just converting between one type to another. So for example, an str function would cast from here an integer to a string. Now for the number data types, so integers and reals, you've got various arithmetic operations you can do. Here are the ones you might forget about. So just for exponentiation, quite an awful word, that's just to the power of. So 2 to the power of 2 would be separated by this little triangle called a caret. Now for the division, the normal division is just 1//, also called real division, because it just does the division you would expect. The quotient, shortened to div, is integer division. So this will do the division but always cut off the fractional part. So 15 div 2 is just 7 because 0.5 gets cut off. Now modulus goes hand in hand with quotient. What modulus does, shortened to mod, is give you the remainder. So 15 divided by 2, 2 goes into 15 7 whole times with a remainder of 1. So 15 mod 2 gives you 1. When you're using if statements in iteration, you might use comparison operators. They're fairly self-explanatory, I think. And Boolean, we will look at later in terms of truth tables. But just in essence, right, with and, both sides need to be true for the whole thing to be true. And with or, only one side is needed to be true. They are a common source of errors. The two big string handling operations I would say are substring and concatenation. For substring, you put the string first, then you do a dot, then write substring, and the two values you put in the brackets are the starting index and how many characters you want. So how many you want to continue from that starting index. And concatenation is just putting two strings together. The plus is used for both addition and also concatenation, depending on the data type. Right, variables are identifiers that hold a value that can be changed. So here I've got one variable called variable. That is my identifier. It's just a name we give it, and it has been assigned first of all value 1, then it's been reassigned to value 2 in the next line. And we have constants. Constants are the same as variables, but they can't be changed. So once you assign a value, it cannot be changed, you'll get an error. So we use the const keyword in the exam reference language, and often constants are put in capital letters. Now, when we're getting user input, we'll do something like this first line. We assign the user input to a variable. We might put a little message to the user in the brackets. Now, user input is always a string, so don't forget to cast it to either one of our maths data types if you are going to do maths operations on it later. Here, name should be a string, and so I've left it as it is. So to print, printing is outputting on the screen. Here I've concatenated the string hello with the contents of the name variable. If you wanted to have some randomness in your code, you might use the random function, which is in the OCR exam reference language. You might assign it to a variable, and here it would generate a random number between 1 and 10, including 1 and 10 potentially. Now all of these concepts will be built into wider constructs, a construct being like a block of code essentially, and we've got 3. The first one is sequence, which is our simplest. A sequence block is just where you've got 2 or more lines executed line by line. So all of the stuff on the slide would be an example of sequence because they would just go line by line as the code runs. Whereas the order the lines run in would vary depending on your selection. So selection, we're thinking if statements most commonly. Now if statements are always checked, and they'll look something like this in the exam reference language. So for example, if price was set to 50 in this example, both premium and standard would get outputted because every if statement is checked. And so because 50 is both bigger than 30 and 20, they would both get run. Whereas we can add elifs for more complicated situations. Elifs, or else ifs in reference language, are only checked if previous conditions were false. So again, if I type in 50, the only difference here being I've now got else if and not if. If I type in 50 for price, only premium would get shown here because that gets checked first, and because that was true, else ifs get skipped. We can stick elses as well. You don't have to, by the way, have else ifs and elses. You can just have ifs on their own. But elses will have no conditions and only run if all previous conditions were false. So they're your last resort. They cover every other possibility. You only ever have one else. You can have several else ifs, and you only ever have one if in one selection block. So if price was now 15 at the bottom, basic would get outputted. There's also another more complicated type of selection you may not have come across in actual programming, which are where you've got switch statements. Now these are useful where a variable determines the selection. So here I'm asking the user to select either option 1 or 2. Well, I could just go if option equals 1, do this. But arguably this is a more simple way to do things. Essentially, in the first case, if option is 1, we're going to launch this program, whatever it would be. If option equals 2, we're going to launch settings. And you've also got a default option, which is effectively the same as else. For any other situation, we would print goodbye in this case. So have a pause, have a look at this if you've not come across this before, but it's like an if statement, just relying solely on a variable's value. Iteration is where some code will repeat, And there are two types of iteration, also called loops, count controlled and condition controlled. We've only got one type of count controlled loop, which is a for loop. These repeat a set number of times. And they'll look something like this. Often it's something like a for I in range loop, or in this case for I to something. We also might add in a step to control what I is changing by. But essentially in the first instance, I would be set to 0. As it loops, I then becomes 1, then becomes 2, etc. until it reaches 5. Once it's 5, the loop will end. So we're looping a set number of times, and we can use a counter variable like I to, in this case, output a numerical sequence, or use it in some other output. There are two types of condition control loops you've got to know about. Again, you may not have experienced the second one in particular, depending on your language. A while loop repeats until a condition is broken, whereas a do until loop, also called a do while loop, repeats until a condition is met, which is a subtle difference, okay, but these are relying on conditions, not counts. You use condition control loops when you don't know how many times the loop needs to repeat. So for a password program, the user might get their password right first time, but equally they could get it wrong a billion times. You don't know how many times ahead of time. So you've got to use a condition control loop. Here's how a while loop would work. While password not equals 123, in this particular case, we're going to ask for the password again. Really, really important that you give the user a chance to re-enter, otherwise it becomes an infinite loop. A do until loop or a do while loop, they're the same thing, look a little bit different. The condition comes after the body of the loop, which means these loops always run at least once. A while loop might never run if the condition is false straight away, whereas a do until loop would run at least once. And you can see the condition itself is really the opposite of a while loop. So a while loop is quite negative, a do until loop is more positive, I would say. Now looking at subprograms, also called subroutines, which are named out-of-line blocks of code. Well, a block of code is just some lines of code, and they've got a name. So add is my subprogram in this case. This is a procedure, which is a type of subprogram. Out-of-line means that we generally define these, which is what this is here, usually in a different place to where we actually run the code. We actually run the code when we call them. Okay, so calling them will execute the subprogram. So here I've added print welcome is just saying welcome. I'm actually calling the add subprogram in this final line where I put its name down and give it some values. Okay, so in this particular instance, you'd see welcome because of this print line, and you'd see 25 outputted too. Because we've got what are called parameters, which are variables, a special kind of variable used as an input to a subprogram. You can have no parameters, you can just have an empty set of brackets, but equally you might have, say, 2 in this case. Well, num1 becomes 10, num2 becomes 15, and so what I'm doing is adding num1 to num2, so 10 to 15, hence I get 25 when this is printed. So if we now modify this slightly to have a function instead of a procedure, this is a second type of subprogram which has a return value. A return value is like an output from your subprogram. Parameters are inputs, a return value is output, but it's kept internal. So print is an output to the screen, return is an output to the main program. And so when you are calling a function, you should assign the return value to a variable. So I've set result to be the return value from my function. Then I can print it. This will do the exact same job, I'm just returning and not printing, but I've got to assign it to a variable. Now we have actually got a few types of variable in this code. I've got my parameters, which is one type of variable. I've also got local variables inside my function, and I've got a global variable outside of my function. So local variables only exist when the subprogram is executing and also are only accessible inside of a subprogram. If your code has got lots of global variables, it's generally not very maintainable. Code which is maintainable is easy to understand and easy to change in the future. But there are some other ways to make code maintainable. One of them is just to use many subprograms. So if you're not using subprograms, it makes things harder to test and can lead to more mistakes. Also, if you're consistent in your naming conventions, this relates to your names for your variables and your subprograms. Using sensible names and names which follow the same pattern makes things more readable. Now, all of the examples I've shown of things like loops and selection and subprograms have used indentation, which is a gap at the start of a line. This is sometimes required in certain languages, but even if it's not, having indentation often makes things clearer to look at because you can easily see what lines of code belong to what block of code. And finally, a simple one is using comments. A comment is an annotation in code. It will be 2 forward slashes in OCR exam reference language, and comments can explain what code is doing to make it easier to understand. Data structures are organised collections of items. We've got a couple, but an array is our main type. So an array typically just contains items of the same data type and will generally be of a fixed or static length, meaning once you set it to be, in this particular case, I'm saying it to have 5 items, you can't then add a 6th item to it, it's fixed. So this first line is me declaring an array called scores with 5 items. And in my second line, I'm actually assigning these 5 items to the array. The name of my array is scores, and you can do something called indexing. Indexing is where you use a number to refer to a particular item. So the first item will start with the 0th index, and you should always assume it starts counting at 0 unless you are told otherwise. So in this case, 3 is 0, 53 is 1, 92 is 2. And so therefore when I go print scores index 2, I would see 92 on my screen. You can reassign items in variables, they're not constants. So in my final line, I'm setting 13 to now become 5. If you need to go through all of the items in your array, use a for loop, something like this, where you start with the index of 0 and keep going until you are 1 less than the size of your array. And then you can index using this variable, which is I in this case, and it will show you all the items in that particular array. SQL is for interacting with databases. You've only got to know about SQL Select in this paper, which is used to search and retrieve data from tables. So here I've got a sample table. A table is built up of several fields, a field being a column, and here I've got 3 records, a record being a row. Select has 3 parts to it. Select the fields from the table where the condition is whatever the condition is. So the last bit's really like an if statement effectively. Here's an example. Let's say I want to select the exam code and the exam length from the exams table, but only where the exam length is less than 130 minutes in this case. Well, that's what I'd write, and it would give me just 2 records because only the first 2 records have an exam length of less than 130. If you see an asterisk in SQL, that means select all, by the way. Arrays can get trickier because you can have 2D arrays which are useful for representing tables, so fields and records. Here is a 2D array which matches my table in the top right. A 2D array is just an array of arrays. So if you see here, I've put it over 3 lines, but I've actually got 3 arrays in a wider array. You can see I've got 2 brackets at the start and end. And these look a bit scary sometimes, but they are only a tiny bit harder because all you need to do is index with 2 numbers and not just 1. The way this will look in exam reference language is with a comma between the 2. So if I'm printing exams 1, 2, the first number refers to which array within the array it is. So it's index 1 here, so it's not my first array, which is index 0. It must be my second one. And then the second number, which is 2 here, refers to inside that particular array. And we've got 0, 1, and 2. So 90 would get shown when I index it like this. If you are wanting to save data permanently, you might use an external file. And before you do anything to it, either reading or writing, you need to make sure you open this file, which means assigning it to a variable and putting down the file name. Now, you also need to make sure when you're done with either writing or reading, you close it. If you don't close it, it can cause errors like corruption, and also it might not actually fully write to it. And between the 2, you're going to be either reading or writing or both potentially, as I'm here. This line is writing a new record to this file. Again, a record kind of being synonymous for a row or a line in this case. So write line just produces a new line in that file. And here I'm reading from the file, so .read line will give you the next line in the file. This while loop is a way that you can get every line in the file because you keep looping until the end of file has been reached. Now, to be a good programmer, you are meant to show defensive design. And this is all about trying to make your programs robust. A robust program won't crash, it won't have errors, and it will be reliable. And the whole point of defensive design is users cannot be trusted. You've got to anticipate misuse. You've got to assume they're going to do some things wrong. And you will check how robust your program is through testing. There are 2 types of testing. Most big projects will use a bit of both. Iterative testing is where you test specific modules while you are developing. So a module could be a subprogram or several subprograms or a particular file, but only a chunk of your code as you are developing the whole program. And any issues found will hopefully get fixed, and then you should retest the module, which is where the iteration comes in. You repeatedly test stuff until it is all perfect. Terminal or final testing comes right at the end, so you test the whole program, not just chunks of it. It won't just be one massive test, it will be broken down, but you're testing how things work together right after development. Errors cause issues and should be found during testing. A syntax error is where you've not followed the rules of your language, you've missed off a colon, you've put it in lowercase when it should be uppercase, etc. And so the code won't even run. Whereas a logical error, the code does not do as you intend. It does run, just it doesn't quite do what you want it to do. And part of your defensive design should be validation. Validation is enforcing a rule around user input, and the rules can vary. Most often this will be a while loop, so you keep asking for user input until the rule is met. Here the rule is that the name has to be more than length 0. You've got to put something in, you've got to enter a value. Authentication is also often done with while loops, quite honestly. Authentication is checking the identity of a user, and the most common way you'll do this is through password checkers. So again, asking for a password, checking if it's correct, often using a while loop. And when you are doing testing, either iterative or final, there should be a range of test data used, not just normal data, which is what you would expect typically, but boundary data, which is sort of on the edge of being allowed, maybe just inside, just outside that boundary, and also invalid or erroneous data should be tested too. So if this is completely wrong, it will probably break your program unless you've got checks in place. Now, invalid tends to mean it's the correct data type, just completely wrong, whereas erroneous is usually the incorrect data type and completely wrong. So they're both wrong, but just different data types. We've touched on this a bit already, but Boolean logic is its own separate topic in this paper too. We've got 3 Boolean operators, and you've got to know the logic gate symbols for these and the associated truth tables. So the symbol is representing the actual circuit called the logic gate. A NOT gate is a triangle with a tiny circle at the end. And a truth table shows all the combinations of a particular circuit. Here, I've only got one input, A. It's either going to be 0, false, or 1, true, and NOT just flips this input. AND has 2 inputs and 1 output, and it looks like this. And the truth table is something like this. So you can see it's always 0, unless both inputs are 1. Both sides need to be true, in other words. And OR is the same symbol as AND, just with a kind of curve to it. And this time, it's only going to give you 0, or give you false, if both inputs are false. One slight thing just to memorize is a few different names for these, or a few alternative names. So NOT is also called negation, AND is also called conjunction, and OR is also called disjunction. The last topic has 5 kind of theory bits to learn about different languages and translators. You've got, first of all, 2 types of programming language, high level and low level. High level languages are like written English. They're more readable than low level languages and easier to code in. They're portable, which means you can write the code and it can run on many CPUs. But because you've got to translate it, these are slower than low level to execute. Things like Python and C# and Java are high level. Whereas low level, we've only really got 2 types, assembly code and machine code. Assembly code looks a bit like this. It uses bits of English, but not much. And machine code is just totally in binary. Now, assembly code is linked one-to-one to machine code, so they're very, very close to each other. You've got more control when it's low level. It's easier to optimize. You might be able to make it go faster when it runs. The downside being these are specific to particular CPUs and harder to write. And so therefore, we do generally use high-level languages. But to use those, we've got to use translators. A translator is a program that converts one language to another. And only machine code doesn't need to be translated to run. A CPU can only execute machine code. There are 2 types of translators which go from high level to machine code. A compiler produces an executable file when you finish the translation. It produces a file which you can run and the program will work. This means you don't need any source code. The actual program code isn't needed as long as you've got that executable file to give to your user. And compilers are fast to execute. You just run the file. The downside being errors are only shown right at the end, which can be frustrating because it might take 5 minutes to compile and you only see the syntax errors right at the end. Whereas interpreters work by translating an instruction, then running it straight away. So you don't do it all in one go like a compiler does, it's done line by line, essentially. The downside being when you give it to a user, they've got to have the source code to run the program, so they get to see what you coded, which makes it hard to sell. The benefit for development is that you see errors as soon as they happen because it runs the instruction as soon as it's translated. But interpreted programs are slower to execute overall. IDEs are the last thing to cover, integrated development environments. They're there to support you programming, something like idle or similar programs. They provide several features. First of all, an editor, you can type the text and it does things like syntax highlighting. It might show you errors, sometimes it might have line numbers, which is helpful. It also can provide error diagnostic tools, at least the more impressive IDEs can. Things like breakpoints, where you can stop the code at certain points to inspect what's going on. They've got a runtime environment, meaning you can run it inside the editor. In idle, you just click run and it runs the code. And to do this, it has to have a translator, and so often these IDEs have a translator built in, so the code can be run more easily. And that is all the content for paper 2. Hopefully that was useful, and I hope the exam goes really well.